So last time we talked about atomic history and atomic structure, and also where the subatomic particles are in the atom, and we talked about isotopes, and I think that's where we left off. So I wanted to go ahead and go back to an example in your textbook, example 2.3. And so here it is in your textbook. They're talking about iodine and how it's important that we get iodine in our diet, and it's added to certain foods. Here you see a picture of iodine being added to salt, and it's important because if you don't get your iodine, you can end up having an enlarged thyroid. And so a question asks, how many protons, neutrons, and electrons would iodine have? In this case, the iodine atom says atoms are added as anions. And so we know anions have negative charges, and it says that this iodine ion is going to have a -1 charge. So we have to figure out the number of protons, neutrons, and electrons in one of the iodine anions. So here, going back to the PowerPoint slide, here's my periodic table. They told us we need to look for iodine, and so if we look on the periodic table, if we zoom in here, we see iodine has an atomic number of 53. So since it has an atomic number of 53, then the number of protons for iodine should be 53. Okay. It should also have 53 electrons if it's a neutral atom. But remember that they said this this iodine ion is going to have a -1 charge. It's an anion with a -1 charge. So it doesn't have 53 electrons, it has 54. Okay, because remember, we're adding electrons, even though it says 1-, we're adding electrons, and minus just indicates the charge of the particle. So it's added an electron here, and then to find the number of neutrons, we have to take the atomic mass. Well, it told us what the atomic mass was of this isotope. It has an atomic number of 127. So going back here, so we take the atomic mass and then subtract the atomic number from it to get the number of neutrons. And so in this case, this iodine anion with a -1 charge would have 74 neutrons. So going back to our PowerPoint here, before we left off on Wednesday, we were talking about isotopes and isotope notation, and that talking about different isotopes, we know that the number of neutrons differ between isotopes, but the number of protons stay the same. And so that means that the atomic mass is affected when we talk about isotopes. So when you're talking about different isotopes, you normally just mention the mass. So for example, magnesium 24 versus magnesium 25, you would talk about them based off of their mass numbers, okay, indicating that magnesium 25 would have 1 more neutron compared to magnesium 24. Magnesium 26 would have 2 additional neutrons compared to magnesium 24. Sometimes you will see at the bottom, using isotope notation, at the bottom here as a subscript, you would see an atomic number. But it becomes redundant because it's the same thing for all 3 isotopes. And so sometimes you're not going to see that. And all you have to do if that information is not given to you is just, again, look on the periodic table, look for the atomic number of magnesium. So if I were to do that here, I would go back to my periodic table, zoom in, and look for my atomic number here for magnesium, which would be 12. So the atomic number for these magnesium isotopes here would all be 12s. okay, indicating there are 12 protons. Sometimes you see it there, sometimes you don't. So I'm just warning you because in chemistry you're going to see a lot of different variations depending on your resource. So if you go online and look things up, it might look different, but that information should be there. The atomic mass should always be there. The atomic number may be there, but it may not be. All right, so if you look here, again, looking more closely into this type of notation, you see the mass numbers on top here. We have helium-4. Its atomic number is 2. It's not always shown, so they're saying here, often omitted. If it has a charge, it is going to be on the right side, and the charge is always after the number, not before. Now, you may see me write it before. That's just because I'm like you, I've done math mostly, more so than chemistry all my life, and so it's just sort of a bad habit. But in chemistry, we normally will write the sign after, and that's indicating the charge. Okay, it's not indicating you have like 2 of something. It just indicates that you have basically 2 more protons, positively charged particles, compared to that of electrons. Same thing for this example here, magnesium 24, this isotope of magnesium 24, it has atomic number of 12, and it has a +2 charge, meaning that it has 2 more protons compared to electrons. All right, so if we look at a table here for hydrogen, hydrogen has 3 different isotopes. Okay, we have hydrogen 1, hydrogen 2, and hydrogen 3. And so there are some common names for these. Protium is the more common type. How do I know that? Well, if I look at the percent abundance here, natural percent abundance, 99.989% of hydrogen 1, of all hydrogen is hydrogen 1. So if I took a sample of hydrogen, 99.989% of it would be hydrogen 1. Hydrogen 2, or deuterium, has a natural percent abundance of 0.0115. So that means you have, if I had a sample, again, example of hydrogen, I would have 0.0115% hydrogen 2, or deuterium. And then tritium, H3, there are trace amounts there. Okay, so very, very small amounts. Okay, and in this table here, you see the atomic numbers are all the same because we know the number of protons never changes. No matter what type of isotope we're talking about for hydrogen, it will always have 1 proton. Okay, atomic number is 1, number of protons 1, that doesn't change. Number of neutrons varies, right? These are isotopes. It's a definition for an isotope. For an element, the atom has a different number of neutrons comparing one isotope of an element to another. Like hydrogen 1 has a different number of neutrons compared to hydrogen 2. All right, so something interesting here, protium is the only isotope known to have like 0 neutrons. Okay, a lot of times they call them protons because it's just a single proton. That's it, and it does have an electron too. But if it's a proton, technically it lost this electron, so it basically only has a proton there. So hydrogen is unique, and we're going to learn how to calculate the average atomic mass. So you see the masses here for hydrogen; they're all different. And the units here are atomic mass units, which we defined earlier. So roughly 1 atomic mass unit is assigned for each proton and each neutron. Okay, so each electron weighs far less. We said about 2,000 times less than the mass of a proton or a neutron. So we don't really count the number of electrons in terms when we're trying to figure out the mass. So in terms of mass, we don't really care how many electrons there are, because if you add a very small number to a larger number, it's not going to really change that number at all. So the atomic mass of a single atom in EMUs is approximately equal to its mass number. So most elements exist naturally as a mixture of 2 or more isotopes, and that's definitely true. So we see that because if you look at the atomic masses, they're all not whole numbers, but and that's because, again, those are average atomic masses on our periodic table. The periodic table lists the weighted average mass of all the isotopes present in a naturally occurring sample of that element. So how do we calculate average atomic mass? So we have this handy equation here. It should be on your test formula sheet. To calculate the average atomic mass for an element is going to be equal to the summation of the products of the fractional abundance for that isotope times its isotopic mass. All right, and so we're going to do that for each isotope. We're going to add up the products of the fractional abundance times the isotopic mass. And once we do that, we can figure out the average atomic mass from that calculation. So here's an example they have for you. For boron, there are two isotopes there. Boron 10 has a percent abundance of 19.9% and a mass of 10.0129 AMUs. And then boron 11 has a percent abundance of 80.1% and atomic mass of 11.0093 atomic mass units. So to calculate the boron average atomic mass, you have to multiply the fractional abundance. So here what they did, they took 19.9, divided it by 100, or the trick is to take the decimal point and move it 2 places to the left. That's basically dividing it by 100. And so they did that here. Then they multiplied the fractional abundance times the isotopic mass. So for boron 10, it's 10.0129. Okay, and then they did that again for the second isotope, same process. So they took the fractional abundance, divided it by 100. So 80.1 became 0.801 times the isotopic mass, which is 11.0093. Okay, they added up the products here. We get 10.81 atomic mass units. All right, so now I'm going to show you a couple other examples that are in your textbook. So it says here, it says, see example 2.4 and check your learning. So see the textbook. So we're going to move over to our textbook here. So let's scroll down here to example 2.4. There it is. All right, so it says a meteorite found in central Indiana contains traces of the noble gas neon picked up from the solar wind during the meteorite's trip through the solar system. Analysis of a sample of the gas showed that it consisted of 91.84% neon 20. Its mass is 19.9929 or 24 AMUs. Neon 21, it has a percent abundance of 0.47%. Its atomic mass is 20.9940 atomic mass units. And then neon 22 has a percent abundance of 7.69%. It has an atomic mass of 21.9914 atomic mass units. What is the average mass of the neon in the solar wind? So here's the solution, but I want to go ahead and show you the solution as I sort of worked it out on paper here. And so what I did was I wrote down the information they gave us. Okay, so they gave us neon 20, and it has percent abundance of 91.84%. Its atomic mass is 19.9924. Neon 21, 47%. Its atomic mass is 20.9940. Neon 22, its atomic mass or percent abundance is 7.69%, and its atomic mass is 21.9914. So here's a formula to calculate our average atomic mass. And so what I'm going to do to figure out the average atomic mass, I take my percent abundance of the first isotope, so for neon 20, 91.84, divide that by 100, or just move the decimal place over 2 places to the left, multiply it times the atomic mass for that element, okay, and do that same process for the other 2 isotopes. All right, so the percent divided by 100 times the mass. Do that again, percent divided by 100 times the mass.